Okay, so we're going to talk about oceans for a little bit here. So this is Ocean 1, Your Ocean. So you can do, along with this, you can have the Your Ocean activity sheet that's in the OneNote. Goes right along with everything we're going to talk about here, hopefully. So maybe just take a second to think about this. What does the ocean mean to you? Maybe consider these things here. What moves from you to the ocean? What moves from the ocean to you? Could be anything you want here. So you don't necessarily have to write any of this down, but later you'll reflect back. Maybe you'll have a different thought on this. So we're going to watch something here by a scientist called Sylvia, named Sylvia Earle. So there's just a few things about her. This is also on the sheet that you're looking at. If you've heard of Jacques Cousteau, probably the most famous oceanographer, and then after him, probably Sylvia Earle, as far as being well known outside of the oceanography itself. So here's a relatively famous quote from her. Even if you never have the chance to see or touch the ocean touches you with every breath you take, every drop of water you drink, every bite you consume. Everyone everywhere is inextricably connected to and utterly dependent upon the existence of the sea. So just consider that for a minute, see how you feel about that, and then you can think about it again after you watch this video. So while you're watching the video, so these are the questions that are on the sheet that you're probably looking at simultaneously. So you can answer these afterwards if you want, or before, or during or after, and then you'll reflect back on that one. So this is it here. It's called My Wish. So the link is there. The link is in the slideshow. If you're looking at the slide, the link is on the page that you're looking at as well. You just click on that. We're not going to watch it here within this video because I think it's about 18 minutes long, and that'll be make this extra crazy long. So watch right there. Okay, that's her. That's Sylvia Earle. So it's a TED Talk. So take a break from this, go watch that, and then you can come right back here. Okay, so you just came back from watching the Sylvia Earle TED Talk about her wish. A lot of good things there that hopefully you picked up on and noticed. You're answering these questions, or else you already have. I'll be interested to hear your thoughts before and after the video there. If you did that, that would be good. So, also important with the oceans is climate change. Largest carbon sink on the planet, meaning it absorbs more carbon than anything else by itself. So there's a little graphic of the carbon cycle, or how carbon travels around. Remember the law: nothing's ever created or destroyed, just transferred from one thing to another. So carbon just cycles through the environment, and the oceans are absorbing lots of carbon. Ultimately affecting climate change. So we could say, are there other possibilities for the climate changing other than the carbon input? Some of these ideas are thrown out. The solar output change, so the sun changing in brightness and how much energy is sending away from it, doesn't seem to be much in the line of legitimacy there as far as being accurate with climate changes. Something called the Milankovitch cycles. recent years they sort of they've talked about this for a long time. Recent years, I think they're moving away from this being any possibility, but it just really talks about um, the orbits of the Earth around the sun, whether it's highly elliptical, and maybe it changes over time, and sometimes we do have an elliptical orbit, like we talked about with the seasons. So sometimes we're closer, not nearly this drastic, but maybe it changes over time when we get farther away and colder, right? Um, or the tilt, maybe the tilt changes over time, the obliquity, which is just tilt, precession of the axis. So we do see the axis precessing. So think of like a top slowing down, spin a top, and as it slows down, it kind of does that wobbling like that. So we see that over time. So maybe that has some impact on the climate over the years. Here's an interesting one you hear every now and then. Over the years, we know we've gone through glacial periods and interglacial periods, and we're currently in what's known as an interglacial period. So maybe we're still just coming out of the most recent ice age where humans have, the whole time humans have existed, we were actually below normal Earth temperature. And now that we're hitting it and going above, we're reacting as though it's a massive climate change. Possible, but I'd say the graphs that we see, the current change in temperature is more steep than we've seen before, and that's the scary part. There's another one they talk about movement throughout the galaxy. As we would orbit the galaxy, maybe we would go through the more densely packed areas, and more cosmic rays would be impacting the planet, maybe even bobbing up and down through the galactic plane there as we go around it. For the most part, all these ideas don't seem as likely as carbon output that they're producing on the planet ourselves. So we could talk about the greenhouse effect. Is it a good or a bad thing? Well, if we're talking about a regular greenhouse, if you've ever been in one, it's very warm inside. So the shorter the visible light rays get through the glass, heat up everything inside, which re-radiate out at different wavelengths, and the infrared can't escape as effectively through the glass, so that all that infrared heat energy just builds up inside. Same thing happens here on the planet. Visible light hitting the surface, warming the surface, re-radiating out as different wavelengths, and the infrared doesn't escape through the greenhouse gases as effectively. Carbon being one of the greenhouse gases, water vapor, methane, are other ones. So still, greenhouse effect, good or bad thing? Well, if we had no greenhouse effect at all, there would be no, the surface of the Earth would be too cold for anything to live on. So we need sun. So our problem is then striking the balance between Mars, which doesn't have enough greenhouse effect, and Venus, which has too much greenhouse effect. Way too much carbon dioxide there, which is way too much of a greenhouse effect holding in massive amounts of heat. The surface of Venus is like 900 degrees, and the atmospheric pressure, I think, is 90 times what it is here on Earth. So if we dropped you on the surface, the heat and pressure would be way too intense. We can't even yet build anything that can last in that environment for significant amounts of time. Conversely, we've got the Mars over here. Potentially both of these a long time ago may have been a lot like the Earth, and then Venus has experienced a runaway greenhouse effect. So we don't want that to happen here. Maybe there were oceans there. There's really no evidence for that, but maybe there were billions of years ago, and then greenhouse effect kicked off and started running away. So as we evaporate more water, it would hold in more heat, which would evaporate more water, which would hold in more heat and evaporate more water, and just cycle around until we have what we have there. So then, as far as our distance from the sun, right, you all know, we're right in between here, right? Neatly, we're sort of the Goldilocks zone, right? Not too hot, not too cold, not too close, not too far away. So we've got lots of graphs like this displaying carbon dioxide concentrations around the planet. This one happens to be in Hawaii because it's out in the middle of the ocean. If we did this here in Baltimore, of course, we would see high levels of carbon dioxide because of all the people living, the factories, and the cars and everything. So this is out in the middle of the ocean where the ocean's absorbing a lot of carbon dioxide. And yet we've seen a vast increase in carbon dioxide over the years. And then interesting, the zigzag pattern, maybe you already know what that is, but what we can talk about is it's seasonal. So every year we have more carbon dioxide and then less carbon dioxide. So photosynthesis is the answer, right? In the summertime, when everything is photosynthesizing and the plants are absorbing carbon dioxide levels go down. Then in the wintertime, when everything is not as green and photosynthesizing, carbon dioxide levels go up. But our general trend then is obviously up over the years. We can look, there's lots of these different places. You can even look in ice core samples. They're actually able to drill ice core samples and go back hundreds of thousands of years and examine the air bubbles caught in the ice and see how carbon levels have changed over the years. Here's our emissions of carbon compared to temperatures. All right, these graphs are all over the place as far as finding them. They're easy to find. And then from our activities, the main one that the main greenhouse gas that we are pumping out is carbon dioxide, as you can see there. Huge abundances since the Industrial Revolution. So things that happen then to the ocean as the oceans warm, as the air is warming and the oceans are warming, the density decreases, thus even constant mass, the volume of the ocean increases. So this is thermal expansion. So the water itself will get larger. So a certain volume of water just warming it up will expand, and like this little graphic here, we take this amount of water and we just warm it up, it'll expand and get larger. So as the water gets warmer, the oceans are rising just from that. But then the other one is the melting of land-based ice. We could also talk about melting a glass of ice water if it was full to the top, and then there's a bunch of ice in there. As the ice melts, the water is actually going to go down because ice expands when frozen, so it takes up more volume. So we're not worried about the glaciers really floating. We're worried about the land-based ice. I should say we're not worried about the icebergs floating in the water. We're worried about glaciers and ice sheets. All of Antarctica is a continent covered in ice. Greenland has a lot of ice. So when all that ice melts and rolls into the ocean, then water levels will rise greatly, as will the water expand. While we're talking about thermal expansion, there's something interesting that water does. One of the few substances that does this, maybe the only one. Everything else we talk about as something that's colder, the molecules will slow down, and get closer together, and actually shrink, right? Be more dense. Water actually is at its most dense at 4 degrees Celsius, right? So if we get water to go from 654, it's getting more and more dense. 4 degrees Celsius, it'll sink to the bottom. So the 4 degrees Celsius water is at the bottom because it's the most dense. Then as it goes to 3 degrees, 2 degrees, 1 degree, and 0 degrees Celsius and freezes, it's less dense than 4, so it actually freezes on top. Other liquids don't do this, just water, which is convenient. If water didn't have this little quirky little thing that it did, then it would sink to the bottom, sink to the bottom, sink to the bottom, and then freeze at the bottom, and then we would have solid ice, right? Be nowhere for living things to live underneath the ice. So, sort of has helped for life to survive on the planet. Interesting. Am I right? Um, Here's a rather dramatic little video of sea level rising. It shows it um, at different amounts of temperature rising, 2 degrees and 4 degrees total global temperature rise. So take a look at some of this. Hopefully. Sorry. So the carbon choices that we make today, that's brings. We should mention this, I guess. So also happening to the oceans, ocean acidification, pretty important. We won't go through the whole process here, but as we put more carbon into the ocean, what ultimately happens, it becomes more acidic, um, and then all the shells, anything that would form calcium carbonate is now struggling um, to build large, good shells, and so they're weakening and they're becoming either weaker or smaller. So any kind of a shellfish is going to be declining, and then our coral and everything, we've seen that happening. So that's also a significant um, something significant that happens from ocean acidification or from carbon being put into the atmosphere. Ocean has absorbing more than it should. So as far as then what we should be doing, there's something interesting to do for you. So your carbon footprint is the amount of greenhouse gas emissions that each individual produces. Can give you sort of a new perspective how much you're really contributing to the greenhouse effect. So you're going to go to this website. This is on the page, okay? And you're going to calculate your carbon footprint. It won't be perfect. It's meant to just give you an idea of how much carbon you're putting out. Obviously, it can't be exact. Right? Every time you breathe out, contributing carbon, there's all kinds of little aspects that we can't really get. But if you work through it, try to do it as carefully as you can. Think about it. I suppose now that this might be easier now that you're not at school doing this, that you're at home, you might be able to get more accurate numbers from where you're living. Okay. So then on your sheet, it has these questions here for you to fill out or to kind of do afterwards and submit. So from this video, you're going to submit 2 things to me, right? The questions from the video, and then your carbon footprint and your responses to these here. Okay. And that is it. You can look at those later. You know what those are. Renewable versus non-renewable. But so you're basically finishing up those 2 things to submit to me.